Hello and welcome to this video from P7 Observing the Universe. Today we're going to be looking at the stars. There they are, look at them, beautiful. And I actually do mean that. I genuinely think there's nothing better in this universe than standing up and looking at the stars. I think that they're absolutely astounding, mind-blowing and amazing. And I strongly urge you to get very far away from a busy town or city, out in the countryside, in another country, in the desert, miles away from any light pollution at all, on a clear night when there's no cloud cover, and look up at the stars and it'll blow your mind clean off. So obviously that might be a problem if you're intending to keep your mind, but seriously, stars are awesome, they're beautiful, and they're amazing. And humans have been looking at them for a long time, and even without using telescopes, this image that you're looking at here is a telescope image, but even without using a telescope, we can tell some pretty cool stuff about them. I'm going to go through quite a lot in this video. I'm going to look at the following things. I'm going to look at what we mean by the celestial sphere. I'm going to look at two measures called ascension and declination. These are ways that astronomers talk about the positions of stars and objects in the sky. This links quite closely with angular size. This is very straightforward. Navigation, quite quickly. A little bit about star rotation. That doesn't actually mean that stars rotate. This is as they appear to rotate. And then we're going to relate this to the universe. So yeah, a little bit to get through. So here we are. You're in my back garden now. So welcome to my back garden. It's got quite a clear night. Nice bit of clouds out. Oh no clouds out. Stars are out. And here we've got the sky, which has got these stars shining through. Now I'm sure that from when you were a kid you'll have heard people, and this is quite a frequent sort of metaphor used for describing the sky and the stars. People say it's like a blanket. The sky is a blanket covered with stars. You must have heard that image. And people talk about the sky in the same sort of way. I mean, for us puny little people standing down on the earth, when we look up at the sky, it looks to us like there's a big roof that's I don't know, like a spherical roof on top of us, and that it's covered with stars, and there's some sort of thing up there that's got stars all around it on a surface. And that's what we mean when we talk about the celestial sphere. This is an extension of what we were just looking at here. The stars in the sky, we sort of see them as covering a surface, and it's useful for us to think about the celestial sphere. Celestial means, I don't know exactly what it means, relating to the sky and to the heavens, and sphere, a circle. So it's to us from our position on Earth. It looks to us like there's a big sphere around the Earth, and it's almost as if the stars are pinpricks on there. Now that's not actually saying that is the case, but that's what it looks like to us. So from anyone doing astronomy on planet Earth, looking up there, we sort of pretend that this sphere does exist, and in doing so it allows us to sort of talk about where they are and do some measurements towards them. I'm just going to explain how those measurements are taken. So same picture, but my version of it, a little bit simplified. I'm going to show you a quick thing about the measuring system, how we identify where these stars are. Now the picture is just a bit unfinished here. Here we've got the planet Earth, and I'm showing the North and South Pole through here, and also across Earth right through the middle we'd have the equator. The equator, of course, is the part of the Earth that's always closest to the Sun as we go around the Sun, and this is the celestial sphere, which I'm just going to call CS because I can't be bothered to write it all the way out. Celestial sphere. And this is the celestial equator, which lines up perfectly with the actual real equator of the Earth, the celestial equator. Okay, now say we are looking up in the sky and we see a star. it would be useful for us to be able to communicate the position of this star to... Why is that disappearing? There we go, there's my star. We see a star, and that's us down here in England, and we're looking up at this star, but we want to describe this star to somebody who lives in Japan, or I want to describe this star to somebody who lives in Australia. And because we're studying the whole of the universe, it's useful to know where is this relative to Earth. So we have a system that allows us to do this. We use two angles. We name two angles in our system, and we have set reference points that we use to describe that. So the first reference point, and to be honest, for this course we don't need to know the origin of this, but there is a reference point, and this is called the vernal equinox. As I've said, you don't need to know this name, you need to know that there is a point though, some reference point in the sky that is a constant that we can measure, and this star we're going to give its position relative to this vernal equinox. And the way that we do that is, let's pick a nice colour. How about an orange? Go for an orange? Alright, agreed. So we want to talk about this star, where is it relative to the vernal equinox, and we do this in two ways. The first angle is given like so. This is the, so from this point along here, we call this the right ascension, A-S-C-N-S-I-O-N. This is the right ascension, and how far up the sphere is this star up here. This is the declination. So any star in the sky at any point, we can say what is its right ascension and its declination, and it's taken relative to one reference point. So that means that, so I've done it for one point here, but let's imagine there was a star here as well. We could also then, what is its right ascension? This going the opposite way, so this would have a negative value for its right ascension. So it'll be a negative right ascension. Whoops, that's not an A. Oh dear. PowerPoint has stopped working. That's what happens when you fail to write an A properly. Okay. How do I delete this now? That's my right ascension, and here is the declination. So this is our reference system. It's like giving a grid reference on a map. You've got your one coordinate going around and one coordinate going up, and that way we can talk about the position of stars in the sky on the celestial sphere. Okay, so we know what the celestial sphere is, we know ascension and declination. What we can also talk about is the angular size of objects in the sky. So let's say that we had let's say that we've got the moon up here. What we can do from Earth is do a measurement, and from my eye here we can measure, and obviously this is what I'm drawing here is quite rough, but we've got an object there, and we can measure what is the angle here, and we can talk about the angular size of an object in the sky. And I have mentioned on a previous video, obviously this is a picture of nighttime, but it could easily be same sky at daytime, and we could have the sun and it just so happens that the moon and the sun have got the same angular size in the sky. They take up the same angular size here. So if you measure an angle, yeah, literally you're drawing what is the angle of that object. Now this, yeah, that's what angular size is. So I don't think I need to say much more. One point though, one small point, is that let's look at a star here. Angular size for a star, and this is tricky because stars are more or less pinpricks. They are tiny, tiny little points of light. They are so incredibly far away, even though that they're probably huge objects. They're so far away that they appear to be the tiniest little points. And this, actually, we're going to come on to this in the next video, but let's say I had a planet over here. Say I had a planet over here. This planet, although very small and to the naked eye it might not be discernible, what we might have is, well, if we were to measure it accurately, or if an astronomer were to measure it for us, we would find a discernible difference. There is some angle here, so it might be that this is something like 0.25 of a degree, and that a normal star is 0.01 of a degree. Now, to your untrained eye, we cannot tell that difference, but obviously an astronomer can. So that's one way that we can identify a planet and see how it's different from a star. All right, so that's some useful stuff there, hopefully. Okay, so here is the celestial sphere again. All right, in the middle, these stars, and what I've got on here, on this picture, is that there's a few constellations shown, and some of these constellations you might recognize. This Big Dipper I've definitely mentioned before, or the Plough sometimes we call it. Cassiopeia or Cassiopeia, I'm never sure how to pronounce that, is quite often visible in the sky here. It's quite an easy one to spot, and Orion certainly is quite easy to see in the United Kingdom. These different constellations are visible in the night sky, and they seem to have set places on our sky, on our celestial sphere. Now obviously they're not all the same distance from us, they're spread out vastly far into space, but to us, it just looks to us like we're looking up at a blanket, and they appear to be dotted on that blanket, on that spherical blanket, in this pattern. Now, it is worth noting that what we see during the course of the year changes. In May, we are going to see Leo, Virgo, Libra and Scorpio up in the sky. Scorpio will just about see, Leo will just about see, but Libra and Virgo will be there. We'll be able to see them really clearly. And other constellations you will not be able to see on the other side of the Earth. Sorry, because those stars are way on the other side of the Sun. So the only time we could see them is if we tried to look through the Sun. So that's during the daytime. These will be out in the day, but we just won't be able to see them because they're flooded by the sun. In the night time we can look out away from the sun and see these stars in the night sky. Later in the year, here, when the Earth has travelled around on its orbit on the other side of the sun, we'll be able to see Gemini, Taurus, Aries and Pisces in the sky. We will no longer be able to see Libra and Virgo and Scorpio because the sun is there, and it's way brighter. These are only up in the sky during the daytime, and they're invisible because they're drowned out by the light of the sun. So this is a phenomenon you might refer to as seasonal skies, and this is again a yearly phenomenon. And some of you will definitely have noticed these names: Libra, Scorpio, Sagittarius, Capricornus it's got here, Aquarius or Aquarius. These are people's star signs, and those who put any faith in astrology will recognize these constellations, and the fact that these constellations are quite often associated with months. What month were you born in? Oh, that makes you a Capricorn. Oh, what month were you born in? You're a Sagittarius. That is based on which constellations are in the sky. And long ago people thought that that was a science, that those stars would have some sort of effect on your personality and your character, that sort of thing. But what is still true, is that at different times in the year, different stars are visible on Earth. And another more artistic way of seeing this is that on the Earth, these are the different constellations that you might see. Now, I don't know how they turn this into a lion. Like, look, check this out. It's just, I suppose that's legs, and that's a head. Doesn't really look like a lion to me. That looks like a. Let's delete this and have a look. But anyway, if you want to believe it's a lion, you can believe it's a lion. That's fine. But my point is, the stars change during the course of the year. Okay, final thing that I'm going to just chat about now is something I've spoken about before. Because the Earth spins, the stars look like they rotate. This is a video that's been taken over the course of the night, and they've been tracking the stars. And because the Earth is spinning around, it looks like the stars are also spinning. So look, we've got planet Earth. Well, sorry, let me rephrase that. Because the Earth is spinning, it looks like the stars move across the sky. So if this is our North Pole, and that's our South Pole, and let's draw in us here in Great Britain, up in the Northern Hemisphere. Right? Ugh, this pen is not doing the business. There you go. Alright, so here we are. And we are going to rotate around like this. And if we look up in the sky, if we're looking in the direction of north but up into the sky, what we would see way up in the sky, way beyond our solar system, looking out into space, is we could actually see lots of stars up here. Now, they're not moving relative to us, but as we move around here, they look like they're spinning, they look like they're shifting. But the star that's immediately above north, well, it always looks like it's immediately above north. When we're here, you look up, it stays where it is. When we move around to here, you look up, it seems to stay where it is, whilst these other ones shift around in this circular pattern. And in fact, stars have been used for navigation. That's not how you spell used, you've got to put an S in there. Stars have been used for navigation for hundreds, thousands of years. Used for navigation for thousands of years by humans. And my favourite star-related navigation story is to do with pirates. And the reason that pirates wear eye patches, they wear an eye patch so that their eye is kept safe and it's kept in dark conditions, so that when you take off the eye patch at night, it's really, really good at seeing stars. And if you've got a really well-trained eye for looking in the dark, you can see stars at night and you can navigate by the stars. And this star in the middle here, this one that doesn't appear to move, that's the one right above north, the pole star, or Polaris. And if you follow this, so if I was here I am, standing outside it says it's the Anglo-Australian Observatory, I'm assuming it's in England, because this would then be the pole star, and if I head in this direction along the ground, I'm going to end up north, going towards the north. So
now it's time for our wrap-up. Let's give it everything we've got. Ready? Begin.
Celestial sphere. Looking up at the sky, it's like we're wrapped in a huge big black blanket covered with stars. And it's kind of useful for us to use that system to describe where they are. We can do well using that system. So we've got our planet in the middle, and it's on a sphere. You pick a point, and you want to say where that point is. Well, let's do how far around is it, how far up is it. We've got our right ascension and our declination. That's a grid system. It's like giving an x coordinate and a y coordinate. It tells us where it is on the sphere. We can describe any point on that sphere using this system. Angular size, how big is something in the sky? Well, let's look how big it is and measure the angle. Easy. Navigation. Some stars are predictable where they're going to be in the sky. Polaris, for example, due north. And because stars are so far away from Earth, their positions really do not tend to change. Well, they spin throughout the sky, but they're very predictable where they're going to be. At different points of the year, we see different things, and this is sort of what I mean here by star rotation. They appear differently during the course of the year, and sometimes what we see is seasonal skies, people refer to. So in different seasons you see different stars because they're in different positions, and we have moved around the sun, and we're looking out at different parts of the universe, which is way beyond us. And I feel at this point I should just give a little, maybe just a really quick picture of the oh dear, quick picture of the universe here. Actually, I'll do a quick picture of the solar system. Here is our sun. This is us, and we're orbiting around it. And very far away from us, in other directions. Now this diagram's rubbish, because if this is the scale, our little planet, that's the problem. There's a problem here, right? I'll be honest with you. It's so incredibly hard to draw this stuff and to imagine this stuff, because the sizes involved are just absolutely mind-blowing. If this is the size of our sun and these are different stars, you wouldn't even be able to see our planet probably. There you go. I'm going to do it tiniest. That's probably too far away. I don't know. We're tiny, and we move on this tiny little orbit around a tiny little planet. No, star. We are a tiny planet, and there's beautiful stars around us. And this is just the beginning. We've worked out where we are. We've worked out about our sun. We've worked out that we move, and we're going to try and just look in the next video at our neighbours, at the other planets nearby. And once we've done that, we're going to look deeper into space. We're going to whip out our telescopes, and we're going to study this universe and get to know what's really going on. And I think it's only fair that since the moon had a few songs played in its honour, that we see out the stars with some nice songs.
And they played and they played. The sky was black and bright with stars.
Twinkle, twinkle,